Today I'm going to teach you the first chapter, which is about Introduction to Heat Transfer. This lecture is for CO1, which is mainly, if you remember, about the concept of heat transfer. Today you will see what is heat transfer. At the end of this chapter, you will learn, you will understand, and you can analyze the heat transfer by those three different modes: conduction, convection, and radiation transfer. If you remember, before we go directly to the heat transfer, we need to have some definitions. In this chapter, we have many definitions, many concepts which are important for your future chapters. As you can see from the title of the chapter, it is Introduction. So you will learn lots of definitions, and you need to memorize them, to learn them for your future chapters as. Here, we are going to mainly discuss about the heat transfer. So what is heat? The first question, the first thing you should know for this subject. It is a form of the energy which can be transferred from one system to another system. So from this sentence, you can see heat is a type of energy. So, and it can transfer from one body to the other body, which this transfer of the heat is due to the temperature difference. This sentence seems to be easy, and you can easily understand what is the meaning of that. But these words, temperature difference, is important. Later, you will see. So for heat transfer, we need to have temperature difference. Thermodynamics. I think most of you have already know about thermodynamics, which is the science of heat and power. But the thermodynamics, which usually is concept about the amount of heat transfer, even in the thermodynamics, we are dealing with the heat transfer, but in the thermodynamic, we had also the power. We also included the power, the work, and so on. But here in heat transfer, we mainly focus only on heat transfer from one system, or from one body to the other one, or from one system to surrounding, or to the other system. And you can see the difference between these two. These two sentences are prepared here to show the difference between thermodynamics and heat transfer. Thermodynamics is concerned with the amount of heat transfer as a system undergoes the process from one equilibrium state to the other one. And heat transfer deals with the determination of the rates of energy transfer and variation of the temperature. You will see how heat transfer is effective on the temperature of the system or body, and you will see we can, if you remember in the thermodynamics, we generally say this much of heat is transferred. We don't talk about the rate of the heat transfer. But here, in heat transfer, we will discuss about the rate of heat transfer. For example, per time, how much heat is transferred per 1 minute, for example. How long it will take, for example, for a cup of tea to cool down. This is mainly related to the heat transfer. And the unit for heat is joule, because as you know, it is a kind of energy, as we discussed here. Sometimes it is called thermal energy as well. But before this, in early 19th century, it was believed that the heat is a kind of fluid, and it is transferred from a body with higher temperature or hot body to cold body. So because of that, we have another unit for the heat or thermal energy, which is calorie. Because in that time, in this century, it was believed that heat is fluid, a substance. But now we know that the heat is not substance, and it is a type of the energy. And this is really important. Heat transfer always occurs from the higher temperature body or a substance or system to lower temperature of an object or to object in contact. So this is important to know. These sentences, these concepts are simple, but you need to know all of them to be able to solve different problems. Heat transfer stops when two medium reach a equilibrium or same temperature. So if we have temperature difference, it will transfer from higher temperature body to the lower temperature. But when they reach after a few time, the temperature of the lower high temperature body will decrease, and the temperature of the lower temperature body will increase. Finally, the temperature of the point to object or to system will be same, which we call that equilibrium state, which the temperature of two systems is similar. And in that time, the heat transfer will stop. Then you can see what is the reason of the heat transfer, which is temperature difference. But how this heat transfer is happen? How this energy is transferred from one place to the other place? As you may know from school things which you already studied, we have it happens in three different modes, which are conduction, convection, and radiation. Today we will go in some detail, not all of the information for them, some detail, and you will see how this heat transfer is happening. And you can see an example of the heat transfer. A cup of tea, for example, or coffee here, it is transfers from this cup to the surrounding. Why we know the direction of the heat transfer first of all, and how we know we have heat transfer? Because we have two objects here, the system at least, the cup and environment, that we have temperature difference. So due to this, we will have a heat transfer. But what is the mode of heat transfer? We will go to next slide to see different type of the heat transfer and how they will happen for a system. And up to here, I told you heat is a form of the energy. Let's go back to the concept of the energy to see more detail about this type of the energy. Energy can have different forms like thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and nuclear. These are all of the forms for energy. And we have a classification for these different type of the energy, and based on that, we can more easily discuss about the energy in the system or change in the energy of the system. We will see the detail for most of these energy in next slide. The first classification is total energy. Total energy is all of the a system or a substance or a material may have some type of these energies together. For example, a system may have thermal, mechanical, chemical, and nuclear energy. All types of the energies which a system may have is called total energy. We show that by capital E, and if we have a system with flow, we can define it based on the unit mass basis. So total energy is the total energy of the system, the summation of all different types of the energy values. And the other classification is internal energy. The sum of all microscopic forms of energy for a system is called internal energy. We will see what are the microscopic forms of the energy. The other, this internal energy is important because we use that, mainly we have only internal energy for the system, and the system which we usually discuss about that, is just a small system or we can't control it, we have the boundary. So usually we don't have macroscopic um, energy for the system, and mainly we have internal energy or microscopic. And simply, this internal energy is usually some of the kinetic and potential energies of the molecules. As I said, internal energy is microscopic. And the velocity and activity of the molecules is proportional to the temperature. So temperature will change internal energy of the system. Here you can see why we are introducing this internal energy, because temperature of the substance or system is reason for heat transfer. But the temperature, how this happens and why this happens, because when temperature of the substance is changing, the internal energy of the system also is changing. It means the velocity and activity of the molecules in that system or in that substance also will be changing. It means it is effective on the motion of the molecules can transfer from one point to the other point. The other definition which you need to know is sensible heat. The kinetic energy of the molecules is sensible heat. Why we call that sensible heat? Because the kinetic energy of the molecule is showing as temperature, change in the temperature of the substance. And the other one, the other definition, which is also really important, is latent heat, the internal energy associated with the phase of the system. If you know or remember, we have different phases for substance or system. For example, we have solid, liquid, and gas. When the phase of the substance is changing, that substance may absorb or release huge amount of the energy. That amount of the energy or thermal energy which is absorbed or released during that phase change process is called latent heat. For example, when we have an ice cube, the melting of the ice, will release energy. This is called latent heat. The temperature of the ice during the melting will not change. The temperature will be 0 degrees Celsius always, but it will absorb energy, and this energy is called latent. The chemical energy which I introduced you in previous slide is the internal energy associated with the atomic bonds in the molecules. If you remember from the structure of the substance, we have molecules and also atoms which are smaller or which make the molecules. The energy between the molecules which keep the molecules in contact or in a certain distance from each other is called chemical or bond energy, or chemical bond energy actually. But the nuclear energy is the internal energy associated with the bonds within the nucleus of the atom itself. So the difference between chemical and nuclear energy you can see here. For the chemical, the energy which keep the molecules together is called chemical energy, but nuclear energy is inside the atom. And we have always this nuclear energy and chemical energy, but sometimes we cannot use them because from chemistry you can find more detail about these two. But what we mainly will deal in this subject is about latent heat, sensible heat, and this type of the energy, or even chemical, which if it is given the energy changing the system, but not about nuclear energy. Okay, now you have seen different type of the energy and how those energy are related to the temperature or heat or thermal energy of the system. Now let's see how these different forms of energy are transferred. Before that, I need to introduce you some concept again. Maybe you recall from thermodynamics or you haven't had that subject. Let me just introduce to you. For to study heat transfer for different system, this word also system is important. System means we select a boundary for what we are going to study. Imagine we have a, for example, imagine this is a tank and we have a liquid inside that. Okay, now we are going to see, the temperature of this liquid, for example, is 50 degrees Celsius. After a while, the temperature will reduce. Why? Because the temperature outside, for example, will be 30 degrees Celsius. Then we have heat transfer from this fluid, from this tank to the outside because of the heat transfer. How we can study this? First, we need to select a boundary and we need to select a system. It is supposed you already know from thermodynamics what is the system and what is the boundary of the system. The system is an imaginary space which we select for our study. For example, we select the boundary of this fluid inside this tank as our system. And we have the boundary here, as you can see, for example. Based on this, we can have closed system and open system. Closed system is like this. The fluid is not flowing, it is stationary. And because of that, we call that closed system or constant mass system. Then we can calculate heat transfer for that later in the. How about the control volume or open system? It is like this, imagine we have a tube, a pipe, a flow is flowing through that. For example, a high temperature liquid. Then temperature of the liquid will be transferred to the surrounding. So here also we have heat transfer, but how we can study the heat transfer or change in the energy for this system? Again, we need to have a system. But this time, the system which we select, for example, this, imagine this is our system. This time, this system will be an open system or control volume. Why? Because we have mass crossing the boundary of the system. We have mass entering to this system. Imagine this is our system. Then energy comes to the system. The fluid comes to the system, and this fluid brings the energy with itself to the system. So it is supposed you already know about that. So simply we have closed system and open system. And to analyze this system, we need to know what is the energy of the system. For a stationary fluid, usually the energy which we have is internal energy. Excuse me. For a stationary system, we have internal energy or U usually. And for a fluid which is flowing, we have enthalpy because we have the energy coming to the system or going out from the system due to this heat transfer. So for stationary fluid, we have U or internal energy. When we have flow energy or flow work to the system, we have PV. P is the pressure of that fluid, and V is the velocity of that fluid. And the combination of the internal energy and flow energy is enthalpy. So for a control volume, the energy of the system is enthalpy of the system, or H equal to U plus PV. And for a closed system, we have U, or internal energy. This is also important for you to know about that later. Sometimes you will see for a system, we just deal with U because we don't have PV. V is 0, for example, for this fluid, then we have only U. And you will see how we can calculate U for a system. The other concept which you need to recall from thermodynamics is specific heat. A specific heat is the properties of the substance. The specific heat is the energy required to rise the temperature of the unit mass of the substance or element by 1 degree. It is the properties of the substance. We need to measure it experimentally, like, for example, color. The specific heat also is the properties of the substance. It is different for different substances. And a specific heat for different phase of the substances is different. The most complicated one is for the gases or some kind of liquid. For the gases, as you know, based on the pressure, the volume will be different. In other words, we have a relationship between pressure, volume, and temperature of the substance. If we compress the gas, the volume will be lower, but the pressure will increase. With same amount, same mass of the gas, if we let the gas to expand, the pressure will drop and volume will increase. So specific heat for gases depends on the volume and pressure of the gas. Based on this, we have two different types of the specific heat for gases. A specific heat at constant volume, or CV. It means, the volume of the gas is kept constant, then a specific heat is measured for that gas. In other words, the temperature of the substance is increased by 1 degree Celsius. The temperature of 1 kg of the gas in constant volume is increased by 1 degree Celsius, and that amount of energy is measured, which is called a specific heat at constant volume. Sometimes the other method is a specific heat at constant pressure, or CP. This time, the volume of the gas can change for 1 kg of the gas, but the pressure remains constant. In this time, the amount of the energy for increase of that 1 kg of the substance by 1 degree Celsius is called specific heat at constant pressure, or CP. These two are important when you are dealing for the gases. Later you will see we need to have CV and CP to calculate heat transfer for a substance, but sometimes you can use CV, sometimes you can use CP based on the system which you have. If you have open system or you have closed system, you need to use one of them. Later you will see which one. And for ideal gases, we have also some extra, information and equation which is helpful in our study. For ideal gases, if you remember, we have this equation: ideal gas law. PV is equal to mRT. This P is pressure, V is the volume, M is the mass of the system, R is the gas constant, and T is the temperature of the gas. For ideal gas, we have this equation. So by this, if we have PV, then and T, for example, or M, we can calculate each one of these parameters based on the other one. So this is also helpful for dealing with the gases. And what is ideal gas? I'm not going to go to details of that. From the thermodynamics, you can recall that. Ideal gases are some gases which we can write this equation for that. For most of the gases in low pressure, we can say that gas is ideal gas. It is a little complicated to prove it. You need to know the temperature and pressure of the gas, then go to the thermodynamic table and compare with the critical temperature and pressure for that substance to be able to say if that gas is ideal gas or not. But simply, you need to know that in low pressures, low pressure means the pressure of the environment, for example, 1 atmosphere, for example, the gas can be assumed as ideal gas, and you can use this equation, especially for air, because for heat transfer, we use air in most of the cases for cooling down something or even to increase temperature of something. And unit of the specific heat are kilojoule per kilogram degree Celsius, or you can see other type or other units for the specific heat. It is important to know these units because maybe you need to use different units in different equations to reach the appropriate answer. What is the relationship between internal energy and temperature change? These two equations, from thermodynamics, if you recall, we have, for internal energy, du is equal to Cv dt. I told you here, Cv is the specific heat for constant volume, and it is the increase in the temperature. So du is the change in the internal energy. So, we have a relationship between the change in the temperature and change in the internal energy of the system. In other words, we say this, if we change the temperature, the internal energy of the system also will change. But if we change the temperature, for example, by 10 degrees Celsius, how much the internal energy of the system will change? Then here we can use this equation. It depends on the specific heat of that substance. If the system is closed system, for example, and we have only internal energy, the total change in the energy of the system is change in the internal energy of the system. So du will be equal to Cv dt. So simple equation, but very useful to calculate the change in the internal energy of the system with changing in the the temperature of it. How about the open system? This time we have enthalpy, if you remember, and change in the energy of the system, this one will cause change in the enthalpy of the system. How much? What is the relationship between these two changes? It depends on the Cp. So dH is equal to Cp dt. In other words, if we know how much is the change in the temperature and we know how much is the Cp or specific heat at constant pressure for that substance, we can calculate the change in the enthalpy for that system. This is the differential form, and we can write this equation by delta or temperature difference like this. Delta U equal to Cv average delta T, and delta H, du is changed to D is changed to delta. It is assumed that we have an average temperature change in the system. Delta U, Cv average delta T, delta H, Cp average delta T. As I said, this average is important. How you can find this average? You need to know the temperature, average temperature. You will see in the examples. To use this equation, we need to have Cv average and Cp average, for example. But how you can find Cv average and Cp average? Cv and Cp for a gas or a substance depends on the temperature of the substance. Then we have thermodynamic tables. We have tables for this. For example, for 10 degrees Celsius, how much is Cv for the air, for example? You need to refer to the table, okay? But for these cases, for example, imagine we have a system, the temperature for that change from 50 to 70. How you can write this equation? You need to find the average temperature, 50 plus 70, 120, then divided by 2, the average is 60 degrees Celsius. So Cv for 60 degrees Celsius should be, we should put in this equation. I hope it is clear. And also, when, this is for unit mass, delta U, the small u, small h, this is for unit mass of the system, okay? But this is for 1 kg, for example, of the system. the change in the internal energy due to the change in the temperature of the system for 1 kg. When your substance is bigger, for example, 2 kg or even smaller, then the mass is also important. For example, you are going to calculate the heat transfer for 1 egg. It is not 1 kg, so this time the mass of the substance also is included. Delta U is equal to mCv, CV average delta T, or delta H is equal to mCp average delta T. I think it is easy to understand. If you have any question during the presentation, even you can open your mic and ask your question. So up to here, you have seen we have CV average, CV, and we have CP for the gases. For the solids or even liquid, which are incompressible substance, this equation will be much simpler. Why? Because we don't have CV and CP. We have only C, or specifically for that substance. Because for the incompressible substance, the pressure and volume usually remain constant during a heat transfer process. So delta U will be equal to mC average delta T. This is for incompressible substances, right? Like solids. As I said, for C, you need to refer to the table. I will show you the tables as well to find C for different substances in different temperature. M is the mass of the substance. Delta T means T2 minus T1. Simply, you can calculate that. C average, you need to know what is T1, what is T2, add to each other and find the average. Then for the average temperature, refer to the table and find C average. So this is for solid and liquid, mass of the liquid. Okay, any question up to here? Class? Are you still with me? Okay, you know, most of the information you have to know, which I have shared, is maybe you are already familiar with them from your school or even from thermodynamics. So hopefully you recall them. But if you have any question about them, please open your mic and ask your questions. Initially, it is easy to understand. As we go further, it becomes more complicated. Hopefully, it will be easy for you to understand all of it. Okay, so you have seen here how the heat transfer, in other words, delta T for a system, can change the energy of the system, delta U and delta H for the open system. Now, let's see, but in heat transfer study, what we are more interested about is not the change in the energy of the system. It's about the transfer, this heat transfer process. Okay, so now we will discuss more about the energy transfer. And as I said, heat is a form of the energy. So energy transfer here basically means heat transfer. Energy can be transferred by two mechanisms, heat transfer or Q and work or W, if you remember from thermodynamics. In thermodynamics, we mainly discuss about both of them together usually, and also usually we were more interested about the work because we wanted to have a machine to produce power, turbine, we had pump and so on. But here we mainly discuss about the heat transfer, the Q of the system. The Q is the heat transfer, which is the amount of the heat transfer, the amount of heat which is transferred actually, or thermal energy which is transferred. The other definition is heat transfer rate. Okay, Q is transferred from or to a system. The amount is Q, but the rate of this heat transfer or heat transfer rate, which means how long it takes to for this Q to be transferred, is also important. How much you need to have, how much you need to cool down, for example, an egg or a cup of tea to then you can drink it. The time is important here for it. So the amount of heat transfer per unit time is called heat transfer rate. The unit is joule per second or watt. And the other definition is heat flux. You know, the heat the heat transfer is Q, the amount of the energy is transferred. The heat transfer rate depends on the duration of this heat transfer, the Q. The other important thing is heat flux, you know, the area, how much energy is transferred in, you know, from a surface, from an area. Why it is important? Because, you know, imagine heat or thermal energy is like different cars, and we have a road. How many roads in the car is, how many cars in the roads are important? Why? Because you can say, okay, how much is the traffic? Here also is the heat flux is important, which is the rate of heat transfer per unit area normal to direction of the heat transfer, like what you can see here. Why this is important? Because, as I said in the example, how many cars can travel through a road depends on the, you know, the width of the road. Here also, how much heat transfer can transfer from a surface depends on the area of the surface. As much as we have a bigger surface, the heat transfer is occurring much easier. And this called heat flux. Heat flux depends on the surface area of the heat transfer. And we have equation to calculate all of these three definitions. Q, or amount of the heat transfer, is equal to the integral of Q dot T from 0 to delta T. In other words, the heat is transferred with this rate, Q dot, for example, 1 joule per second. Then during this time, 0 to delta T, during 10 minutes. Then if this Q dot, you know, this integral form is for the time when the Q dot, the heat transfer rate is changing. Why it is changing? Because, for example, later we will discuss about that more. I'm not going to detail. But if Q dot is constant with time, then we can use this equation to calculate heat transfer. Q is equal to Q dot delta T. Delta T is the duration of the heat transfer. Q dot is the heat transfer rate. How much heat or thermal energy is transferred during a second, for example, as you can see here, joule per second. How about heat flux? As I said, it depends on the area of the normal to the heat transfer direction. So Q dot, the lower Q dot is equal to Q dot, or rate of heat transfer, divided by A. These, you know, these three are important, and you need to do not, you know, mix them, and you need to know each one of them specifically, because in the examples you will see, each one of them may be a question to calculate heat transfer, to calculate heat transfer rate, or even to calculate the heat flux. A unit for the heat flux is watt per meter squared. Okay, here we have an example, a simple example related to what I have already told you up to here. Imagine we have a copper ball. We are going to, you know, the temperature of this copper ball is going to change. We are going to increase its temperature. Let's see how will be the heat transfer for this copper ball. I'm not going to the detail of the, you know, heat transfer mode and so on. Totally here, we just going to see how much heat is transferred. So we have 10 centimeter diameter copper ball, and it is going to be heated from 100 degrees Celsius to 150 degrees Celsius. So temperature is going to increase by 50 degrees Celsius in 30 minutes. So we have time as well. And the average density and specificity of the copper in this temperature range also are given. The density is 8,950 kilogram per meter cubed, and this is a incompressible substance. So we use C for the CP. However, we can also write C only here. Then the C also for this substance is given. For the copper, you can find also in the table, which I will show you. It is equal to 0.395 kilojoule per kilogram degree Celsius. Now we need to determine the total amount of heat transfer to the copper ball. How we know the heat is transferred to the ball? Any idea? Why here we know the heat is transferred to the ball? Any idea, class?
Temperature difference.
Yeah, we have temperature difference. And why the direction is from surrounding to the ball?
It's a lower temperature.
Because the temperature is increased for the ball. The initial temperature is 100 degrees Celsius. The final temperature is 150 degrees Celsius. So it means the energy is absorbed. The temperature is increased, so it means the energy is absorbed. It is transferred to the ball. What you mean is right, but the explanation only need to be modified. Thank you. And so we need to calculate the amount of the heat transfer, or Q, the capital Q. In part B, we need to calculate the average rate of heat transfer to the ball, Q dot this time. And in part C, we need to calculate average heat flux, or lower Q dot. So we are going to calculate this Q dot and this heat flux for this system. So assumption, as if you remember from the thermodynamics as well, or here I'm going to just remind you, assumptions are really important. Without appropriate assumptions, maybe your answer will be wrong. So here, our assumption will be we have a constant property for the copper at the average temperature. Why? Because, as I said to you, for example, a specific heat or even the density of the substance will change with the temperature. You know about the expansion. Expansion due to the temperature. If we increase the temperature of this copper ball, its volume will change due to the expansion by the increase of the temperature. So the density will be different. But here we can assume, or we assume that the density remain constant. So by this assumption, we can solve this problem like this. The average density and the average specificity are already given in the question instruction. In part A, we are going to calculate the average heat which is transferred to this copper ball. Simply, we can use this equation. Q is equal to delta U. Why Q is equal to delta U here? Because, here our system is this ball. And as you can see here, we don't have any flow here, any mass flow here. Here we have a stationary substance. So the change in the energy of the system is only change in the internal energy of the system. So Q is equal to delta U, for changing the energy of the system, equal to mCV average T2 minus T1. This is delta T. Here, what we have T, it is given. T2 and T1 also are given 150 degrees Celsius, 100 degrees Celsius. Why we don't have here is M. How we can calculate that? You know the relationship between the density, mass, and volume. M is equal to, or mass of the substance is equal to the density times volume of the substance. Now we are going to calculate M to put in this equation and then calculate the Q, or heat transfer. Okay, M is equal to rho times pi V. Rho is given again in the equation instruction. How about V, or the volume of the ball? Simply, we have a ball here, we have its diameter, then we can calculate its volume. Pi by 6 d power 3 is the volume of the sphere, or the ball here. So pi by 6 rho d power t. We have rho, or density here. We have d, or diameter, 10 centimeter. We need to convert to the meter, 0.1 meter power 3. Then if we solve, and if we do this calculation, finally, the mass of the ball will be calculated, 4.686 kg. Okay, now we have M as well. Simply, we have F, we have C average, we have T2, T1, substituting this equation, and then we can calculate Q, or the total heat transfer during this heating process. Q is equal to, we have M, now we have calculated here. We have C average, it is given, and we have T2 and T1. So simply, we can calculate Q. What it is important in this equation are units. Be careful with units, kg, kilojoule per kilogram, degree Celsius, and degree Celsius. And finally, the unit for the Q will be kilojoule. The 92.6 kilojoule is required to this for this heating process, or the heating process from 100 degrees Celsius to 150 degrees Celsius. In part B, we are going to calculate the average rate of heat transfer to the ball. And simply, you know that rate of heat transfer means the amount, how much heat is transferred by unit time. So we need to divide the amount, the value of the heat which is transferred during this heat transfer process by the duration of the heat transfer. Okay, we have the Q, or amount of heat which is transferred. We have calculated here. We need to divide that by delta T, duration of the heat transfer. Delta T also is given, 30 minutes. Then Q dot average, or average heat transfer rate, is equal to Q, or heat transfer value, divided by delta T, or duration. Q is calculated, delta T is 30 minutes, or we need to convert to second. 30 minutes means 1,800 seconds. Then we can calculate by this equation the Q dot average, or average heat transfer rate. Again, the unit need to be careful, which is 0.0514 kilojoule per second, or simply 51.4 watt is the rate of the heat, the average rate of heat transfer for this heating process. In part C, we are going to calculate heat flux for this heat transfer process. Simply, if you remember, we have this equation, Q dot average, lower Q dot actually average, which is heat flux, means that heat transfer rate, or average heat transfer rate, divided by the area of the heat transfer. What is the area of the heat transfer for this ball? You know, here we have a ball, it is a sphere. So heat transfer, we assume that is from the surface of the ball. So what this A actually is the surface area of this ball, or surface area of a sphere with this diameter, 10 centimeters. So Q dot average, which is the rate of heat transfer, we have calculated, we have here. How about A, or the surface area normal to the heat transfer? You know, transfer is always normal to this surface of this sphere. So A, or the surface area of heat transfer, it will be equal to surface area of this sphere. Pi d2, or pi d power 2, is the equation to calculate the surface area of the sphere. Pi d power 2, d is 10 centimeter, or 0.1 meter power 2. If we substitute in the equation, we can calculate heat flux, or Q dot, lower Q dot average, which will be 1,636 watt per meter square. Then you can see how we use those equations to calculate heat transfer, to calculate rate of heat transfer, and to calculate the heat flux. And the concept is easy. Hopefully you can solve similar problem by this method as well. And you know, here is a notice which I need to tell you. We have also here an assumption. We assume that heat is heat transfer from the surface of the this ball is is constant, is same in all of the surface of the ball. However, it is usually not like that. For example, imagine we put this ball on the surface of a stove or something. Then heat transfer from the bottom is higher than heat transfer from the top of the ball. Okay, so heat flux from the bottom is higher than heat flux from the top of the sphere. But here we assume that heat flux is same in whole surface of this ball. This is something which you need to know about the heat flux. That was just simple thing, some introduction, and I think most part of that was already familiar for you from your schools and also from the previous subjects. Now, as you know, we have a relationship between the thermodynamics and heat transfer. Because as you may know, thermodynamics means the science of heat and power, and heat transfer means the value related to the heat transfer for the systems. So here I will also introduce I need to introduce you review the laws of thermodynamics, which we can also change them for the purpose of our transfer calculation. If you remember, we have first law of thermodynamics. The first law of thermodynamics is also called conservation of the energy. Based on this law, energy cannot be created or destroyed during a process. It can only change form during a process or transfer, actually. Then, as you can see here, the first law of thermodynamics can be written like this: total energy entering the system which I already introduced you, closed or open system, minus total energy leaving the system will be equal to the change in the total energy of the system, or E in, which means the energy to the system, E out, energy leaving the system, will be equal to the delta E, or the change of the total energy of the system. These energy which come to the system or goes out from the system can be in different form, like heat, work, or mass. So energy can come to the system or goes out from the system by heat, by the form of heat or work or even mass. And the change in the total energy of the system can be in different forms, like the change in the kinetic energy, in the internal energy, in the potential energy, and such other forms of the energy. These called energy balance in normal form, which we which can be used to study the change in the energy of the system due to the this energy which come or goes out of the system. The energy balance in rate form, in other words, for the open systems, is like this: E dot in minus E dot out equal to dE of the system divided by dt. It means, rate always, you need to know that when we have this word, rate means by time. So rate of the energy transfer by heat, work, and mass means by time. How much energy is coming to the system or going out from the system, and by time, how much energy of the system will change. So this one is energy balance equation in rate form. Sometimes we are really interested to know how much energy is transferred. We don't care about the duration of this energy transfer or changing the energy of the system, but sometimes the time, the duration of this energy transfer or changing the energy is also important for us, which we can use this energy balance in rate form. And this is the if we have a steady system, a steady system means the system, the total energy of the system with time doesn't change. In other words, this dE system by dt is equal to 0. I repeat that again. For a steady system, dE system by dt, or the change in the energy of the system, is 0. Then the E dot in minus E dot out will be 0. In other words, the amount of the energy or the rate of the energy which come to the system is equal to the rate of the energy which go out from the system. In that case, the energy of the system with time remain constant. However, we have the energy coming to the system, energy going out from the system. But because, imagine we have a pool, we have water coming to the pool from one side and water which is leaking from the other side. If the flow of these two water is equal, then total amount of the water always remain constant. You can see in the you have this experience in the pool. Always you can see the level of the water is constant because the water is coming to the system and the water which leaving to the pool is same. So in this case, for a steady, the rate form of the energy balance will be like this: E dot in is equal to E dot out. It is important and interesting because we can now use this equation to calculate E dot in or to calculate E dot out for a steady system. And as I said, the energy E dot in can be in 3 different forms: heat, work, or mass. And also E dot out can be heat, work, and mass. And this is for energy balance. In heat transfer problems, we mainly deal with the heat transfer. And we usually ignore work and mass, and we only interested about the heat. If we write this equation, E dot in and E dot out, the energy balance equation, and bring out the heat from that equation, we can write like this. E dot in means Q dot plus Q dot in plus Q dot W dot in M dot in. Okay. Then if we bring out Q in and Q out, we can write like this: Q in minus Q out plus E dot E generated is equal to delta E of delta E thermal of the system. This is not rate form. This is a normal energy balance. And let me tell you, write some detail about that. Here, E dot in, if we write like this, for example, E in plus E out is equal to delta E of the system, this equation. Then, either E in means it, let me just write by Q and so on. Q, W, this in, W in, and mass, ME, okay, plus Q out, we write plus because in this equation, we don't care about the direction of the Q. Later, the value, the amount can be negative when we put here. Q out, W out, M out. No? Delta E of the system. Delta E of the system means the change in the whole energy of the system. It can be delta U, it can be the even delta K, the potential, the kinetic energy, delta P, and so on. What we interested about it heat transfer is delta U usually, or even delta H, enthalpy of the system for open system. So here, if we put all of these W and M together, and we just have this Q in and Q out, and also put the sign for the Q out, then we can write like this: Q in minus Q out, net heat transfer to the system, plus E generated heat generation. This heat generation means can be by work, mass, and so on in the system, will be equal to delta E thermal of the system, change in the thermal energy of the system. This is the equation which we mainly use for heat transfer. This is heat balance for a system. We have energy balance, from thermodynamics. For the heat transfer, we have heat balance equation. We just care about the Q and amount of the heat. Q in, Q out, the heat which comes to the system, Q out, the heat which is out of the system, and generated heat which is generated in the system. Later we will see some example with heat generation. And delta E of the system, only we care about delta E of thermal. It can be delta U or delta P. And this E generation in the system can be due to the different conversion for different type of the energy. For example, the friction in the system can cause the heat generation. The nuclear, reaction can cause heat generation. Even, the electricity flow or current through the wire can generate the heat. Then all of these heat generated can be due to nuclear, chemical, mechanical, or electrical energy conversion to the thermal energy. This is called heat generation, and we need to include in our equation. So this equation is the basic equation for the heat balance and study our system. Now let's see. Let's write this equation for the different type of the system. First, we can write energy balance. Actually here, as I said, we mainly go to, we write the heat balance because the examples which we have here mainly just include the heat change or thermal energy change or transfer to the system or temperature change of the system. And we don't have work in our studies in this subject. So imagine we have a closed system. First, we are going to write energy balance equation. And as you know, the heat balance equation actually for a closed system. A closed system can be like this, a can of the liquid, which we know how much is its temperature, we know how much is the mass, we know its boundary, and we know the mass remain constant during this heat transfer process. Imagine the temperature is 10 degrees Celsius, And after a while, due to the temperature difference between this can and surrounding, which the temperature is 30 degrees Celsius, the can temperature, the temperature of the can or the fluid in the can will increase until it reaches the same temperature with the environment. So we have a closed system, we have heat transfer from this system to the surrounding. So if we want write the, if you want write the energy balance equation for this closed system, we will have equation like this: E in minus E out equal to delta U. Why here? You know, if you remember, we had delta E here, but why we have only here delta U? Because as I said, delta U means the change in all of the form of all forms of the energy. But here we have heat transfer and we have a closed system with fixed mass. Then the change in the energy here is only change in the internal energy of the system. This is a rule, and you can use for all of the closed system. For a closed system, usually the change in the energy of the system is only change in the internal energy of it. So E in minus E out is equal to delta U. And if you remember from the previous slides, delta U during this process will be equal to mCV delta T. CV, why CV? Because the volume remains constant here for the fluid which we have. M is the mass of the fluid and delta T is the temperature difference. So this equation is a general equation for a stationary closed system without any work. We can write Q equal to FCV delta T. Q is amount of the heat transfer or even energy transfer. mCV delta T. How about system with flow or like what I told you, like a pipe with a flow with high temperature inside that? Then the energy balance can be written like can be written by the energy balance equation. But this time we need to have more information. We need to have more information about our system, because here we have mass to the system. Imagine this is a pipe. We have a fluid flow inside this pipe. Then it means, and you know, the temperature, if we imagine the temperature of the fluid inside this pipe is higher than the surrounding, then you will have it transfer from this liquid to the surrounding. But how we can calculate the transfer for this fluid inside this pipe, for example? Here we need to select control volume. Our system will be like this. For example, imagine, you know, this is imaginary boundary for our system. This is the boundary and this is control volume. And, you know, to make it easier, to make our calculation easier, if you remember also from thermodynamics, we assume that here we have a steady flow. What it means, a steady flow? It means the flow rate or the amount of the fluid which come to the system from this side, for example, is equal to the mass, you know, if we have m dot in and here m dot out. For a steady flow system, m dot in is equal to m dot out. In other words, the mass flow rate remain constant during this flowing process in our control volume. This will cause the calculation be much be simple compared to the non-steady flow system. For non-steady system, flow system is much complicated, more complicated to calculate. But fortunately, for most of the systems which we have, for example, heat exchanger, I don't know, many other examples, the system which we have is a steady flow system. So if we learn how to find the heat transfer for a steady flow system, we can use it for many applications. So we select our control volume like this, m dot into the system, m dot out, which is constant. So simply we can say m dot. We have T1, the temperature of the fluid at the entrance of the control volume. T2, the temperature of the fluid at the exit of the control volume. So we have different temperature, T1, T2, during, why? Because of the heat transfer to the control volume or from the control volume. E dot, which is transfer or the energy transfer for our control volume, can be written in the rate form. If we compare this equation with this one, here we have m dot. Usually we need to calculate the rate of the energy transfer. E dot transfer equal to m dot Cp T2 minus T1, temperature at the exit and entrance. Cp, why Cp? Because here the volume is changing constantly, but P remain constant during this process because we have a steady flow process. And m dot is the mass flow rate. We need to know this information to calculate the E dot or the energy transfer rate from this system. So, as I said, let's just go to some details. For the open system, we need to have control volume to select appropriate control volume, which is important. It should be a steady to be able to use this equation. It means no change we try at our control volume actually. The mass flow rate should be given, it is important. M dot, which is equal to actually rho VAC. We need to know this equation because in many cases, the m dot is not given directly. We need to calculate that. Density is the properties of the substance we can measure. V is the velocity of the substance, of the fluid here. And AC is the surface area of the this fluid flow, actually, or the normal surface area for this fluid flow. For example, for a circular tube, AC is equal to pi e power 2 divided by 4 because the fluid is the cross section of the fluid flow is a circle. And volume flow rate, again, by using this equation, actually, we can calculate volume flow rate. Volume flow rate is equal to V dot V times AC. This is volume flow rate, this is mass flow rate. You need to know this information later in the examples. You will see how we can use it. And VAC, or the velocity times the cross-section area of the fluid flow, which is also equal to m dot, or mass flow rate, divided by rho. This is also important equation in the examples you will see. And when, because here we have a flow in motion, for sure the kinetic energy and potential energy will change during this heat transfer process. But the change in the energy due to the kinetic and potential energy is very small compared to the change in the energy in the system due to the heat transfer. So usually we can ignore or neglect the change in the energy of the system due to the change in the kinetic and potential energy of the system. If you remember, here the general energy is delta E system. All of the energy of the system, which is delta K, delta P, delta U, and so on. But here, when we have closed system, kinetic energy, if you remember, kinetic energy 1 divided by 2 and V2. Here, do we have V? No. So K is 0 always. How about P? If you remember, mgh. Here, something is changed? No, just a small can, the distance here, also nothing changed. So delta P also is 0 during this heat transfer process. But what about here? Here we have velocity, and usually in general application, the velocity is changing. So we have change in the kinetic, and sometimes we have a tube and tube is like this, then potential, the flow come to tube, sorry for the drawing, like this, then potential energy, we have delta H here, then the potential energy may change as well. But it is a small, so we can ignore that. So for the control volume or open system, we can write this equation by neglecting the delta K and delta P, and if there is no work interaction, then the total change in the energy of the system will be only due to the heat transfer. Q dot equal to m dot delta H. This time we have enthalpy, or m dot Cp delta T. So for an open system or control volume, we need to use this equation to calculate the rate of heat transfer. M dot Cp delta T. This is the other equation which we need to use to calculate the rate of heat transfer, but this time for open system. Okay, I think up to here is enough for this session.